Hi everyone, I am Dr. Surjit Singh. Today we will talk about the Leetcode problem on flip equivalence of binary trees. Let us begin. We are given roots of two binary trees in which node values are all unique and lie between 0 and 99. We are to find if they are flip equivalent or not. Flip equivalent means that either two trees are similar to each other or for some of its nodes, the left and right subtrees have been interchanged. This is a fairly simple solution and we learn about generators. Consider the two trees for which roots are given. They are exactly same, hence they are flip equivalent. When we flip the right and the left children of one of the nodes of one of the trees, the two trees remain flip equivalent. However, these two trees are not flip equivalent because the values of some of the nodes are different. These two trees are also flip equivalent as none has been interchanged with 2 and these two trees are also flip equivalent. In one of these trees, left and right subtrees of node 7 have been flipped. It is clear that recursion can be used to evaluate the two trees. Let us first consider some edge cases. If both root 1 and root 2 are same, they both refer to same object. It means a single tree is considered twice. In this case, the two are flip equivalent. We need to check this because if both of the roots are none, they are flip equivalent and we return true. On the other hand, if only one of the two nodes is none, or if values of the two nodes are different, then the two trees are not flip equivalent and the answer is false. We enter recursion phase only if neither of the two root nodes is none and their node values are same, in which if left subtree of root 1 is flip equivalent of left subtree of root 2 and right subtree of root 1 is flip equivalent to right subtree of root 2, or if left subtree of root 1 is flip equivalent to right subtree of root 2 and the right subtree of root 1 is flip equivalent to left subtree of root 2, then the two are flip equivalent, otherwise not. Note that the next level of recursion will take care of cases like this and this. If the nodes are not equivalent, the function will return false. For example, in this case, the edge case will find that the two values are different and it will return false and further recursion will stop. We can appreciate the strength of recursion in handling such problems. It makes programming very simple, systematic, and interesting. If n1 and n2 are lengths of the two trees, time complexity is minimum of these two numbers in Python language. If h1 and h2 are the heights of the two trees, in Python the space complexity is minimum of h1 and h2. We will traverse the two trees in such a way that the child with smaller val is traversed before the one with bigger val, and therefore the traversal result will be same for all the flip equivalent binary trees. Let us understand this with the help of an example. We are given these two trees. Let us consider the first tree and understand how we can use generators to produce iterables. Here we will implement DFS as a generator. Let us define a list named list1. We will use this list to collect tree nodes values in the traversal. In the first call to the generator named DFS, root 1 becomes the node. If the node is none, this function does nothing and returns nothing. But 4 is not none, so we yield node value that is 4. It is passed to the main function as x. Note, yield is different from a return statement. Return statement terminates the execution of DFS function, whereas the yield statement only pauses the execution of the function. Yield returns a series of values that can be used just like the values provided by an iterable. In the second iteration of X, DFS will resume execution from the statement from which it had yielded the value. Upon yielding 4, control shifts to the main function where we append the yielded value to list 1. The first iteration of X is now over. In DFS, we now extract values from the left and right child nodes. This value is -1 if a child node is not present. We compare the two values and first process the smaller node. As 2 is smaller than 7, we process the left node before the right node. Present call of generator function is suspended and we make another call to DFS for which node is equal to 2. Further yields of X will be from this new call of generator. Yield from statement allows recursive calls of generators. First statement in this call of DFS is yield node, which sends value 2 to X, which is appended to the same list, and we go back to DFS. Remember that list 1 is defined outside of DFS and is common to all calls of DFS. Both the child nodes of 2 are none, so their values are -1. Next call gets none as node. However, DFS function works only if node is not none, so it comes out without yielding anything. Right node is also none, which also fails to yield any value for X. Last statement after processing both the children of 2 is to yield a flag to indicate that processing of this node has ended. X becomes hash character and we append it to the list. We now resume with the processing of node 4. We remember that its smaller node has been processed. We now process 7. Its first statement yields 7 to X, which we append to the list and go back to resume processing of 7. Its two children are 1 and 5. We process its smaller child, which is 1. In the first statement, we yield 1 to X and append it to the list. Both the nodes of 1 are none, which yield nothing. In the last statement of 1, we yield hash to X, which is appended to the list, and this call of DFS ends. Next child of 7 is 5. Processing of 5 yields 5 and hash to X. DFS of 7 now yields hash, which we also append to the list, and this call of DFS also ends. Last statement of 4 yields yet another hash. There is a hash at the end of every node, so we get 5 of them in the list. This marker is necessary because the number of children of a node in the two trees may be different. Hash ensures that processing of a node has been finished and no other child of the node is present. After the end of DFS generator function for root 1, no more yields are possible and we come out of the for statement. We will now get a similar list for the other tree. But this time we will learn to combine three statements into one. We are using the same generator for root 2 this time inside the definition of list 2. The X items appended in list 2 are those which we retrieve from DFS for root 2. Let us now revise the statement for list 1 also in the program. Both of them are now single line statements. As smaller child is always processed before the bigger child, the two lists are always exactly same for the flip equivalent trees. The problem now reduces to comparing these two lists. Note, let's talk about the importance of hash. We can see the lists for these two trees. Without hash, both the lists will be same and the conclusions will be erroneous. All function is useful for comparing two lists. We zip the two lists using the zip longest function. In a zip statement, each pair of items in the two lists are converted to the list of tuples. Longest ensures that if one of the list is longer than the other, none is added to the smaller list. list of tuples produced is always iterable. In the first iteration, pair is 4 and 4, so x equal to y gives true. In the second iteration, 2 equal to 2 is also true. Final result is true when all the tuples have matching pairs. In the present example, the final result is true, which means that the two trees are flip equivalent. If there is even one mismatch, the all function returns false and further processing stops. Further, we do not have to save the lists in memory. We can use them in situ, which means that we use a product as and when it is produced. The generator DFS functions now become parameters of zip statement. An advantage of this is that as soon as a mismatch is found in the trees, further processing stops and we do not have to traverse entire trees and generate the full lists. To summarize, there is no limit to how brief we can make a program. There is always a trade off between efficiency and simplicity, clarity, and brevity. In Python, time complexity is minimum of the sizes of the trees because processing stops as soon as a mismatch is found in the lists. In Python, the space complexity is the smaller of the heights of the two trees. Thank you for your time. Please stay tuned for more such videos.